Now we've already proven this compound angle formula, and we've done that taking a little bit of time and effort over it, because once we've got this one, we can actually generate the other 5 from this. Now we can get 3 of them quite quickly and easily just by replacing negative beta with beta, and vice versa, beta with negative beta. But we need some other tricks up our sleeve when we want to change the cos formulas into sine or tan. So we'll see there's a different method for each of those. So the best one to start with is the one that looks exactly like the one we've got, except that negative beta has become beta, so in turn beta needs to become negative beta. So the way to do it is just to write out what we already had, but instead of the betas, we're going to put negative betas in. So we end up with cos of alpha, cos of negative beta, plus the sine of alpha, sine of negative beta. Now, that looks awkward. Can we tidy it up? Well, we can, but we need to explain why and how we did it, because this is a proof. So at that point, I'd say, but the cos of negative beta equals the cos of beta. Now, why does it? Why does that equal that? It's because y equals cos beta, or cos of anything, you could write cos of x, cos of theta, cos of whatever you want, is an even function. Now, the fact that it's even, we don't really need this in our proof, but just so we're thinking about what this really means, we know that the cos of, say, 30 degrees is equal to the cos of, say, minus 30 degrees. We've considered that already. You get the same answer from both. So the cos of minus b and b is the same, or beta and minus beta. So therefore, we can tidy this up even further by replacing cos of minus beta just with the cos of beta. Now, what can we do over here? We've got the sine of minus beta. Can we replace that with something? Well, we can, but we need to replace it with something different. Let's consider the sine of minus beta. What does that equal? Now, thinking about the sine curve, it's an odd function. And that means that if we've got the sine of some negative number, let's pick something we're familiar with, like negative 30 degrees, say, that would be a lot like the sine of 30 degrees, but negative. So it's equal to the negative sine of beta, isn't it? Because y equals sine of beta is an odd function. Okay, you can save a bit of time there. So those statements are kind of necessary for explaining why we were able to make this switch and why we were able to make this switch. So now we can go ahead and make those switches. We've got, therefore, cos of alpha plus beta is equal to cos of alpha, that didn't change. And this is just cos of beta now. But here we've got sine of alpha, and this is now negative sine beta. So we want to write the sine beta here, but the negative can come all the way out the front there, and we end up with that negative sign. Now, this makes a lot of sense. So when we look at the finished result, we can see that this one and this one have a different sign in them, and the only sign that's actually in the function itself has also changed. But it's not enough to just say, I'm going to switch that for a plus, so I need to switch that for a minus. You need to actually go through this process of making the switches and then explaining why they can either stay the same or why they become something slightly different. Now, proving sine of alpha plus beta is a little bit trickier. We actually need this identity to be able to do it. Now, we've seen this identity a bunch of times before. We know that in any right-angled triangle, if you call one angle here theta, then the other one must be 90 degrees minus theta. And now that we're calling 90 degrees pi on 2, because we're working in radians, we can see that this angle must be this. So obviously, if this is 20, this one will be 70. If this is 30, this one will be 60. In other words, they add up to 90 degrees. And when you know one, you can find the other by doing 90 degrees minus that. So we already know this identity works. So if we want to start with this one and change it to the cos of something, now why would we want to do that? Well, because we've already proven this one. We know how to find the cos of one angle minus another. So let's change this. Now here, just as we took whatever theta was and we did pi on 2 minus that, here we need to do pi on 2 minus whatever theta was, the sine of alpha plus beta we're working with in this case. Now we're subtracting alpha plus beta, so we need to carefully put it in some brackets here. Now I can expand those brackets out and say that we've actually got the cos of pi on 2 minus alpha minus beta. Okay. Now, what are we going to do with that? Does it look anything like this? It does, doesn't it? But instead of grouping these two parts together, now we can group the first two terms together and say that's actually the same as the cos of pi on 2 minus alpha as a single entity minus beta. And now we've actually got it into this form, we can just go ahead and generate this, where our first term, or our alpha, is actually pi on 2 minus alpha, and our beta is just still beta. So anywhere they've written alpha in here, we want to put pi on 2 minus alpha, and away we go. We can say that this is now cos of pi on 2 minus alpha, cos of beta, plus sine of, not alpha, but pi on 2 minus alpha, sine beta. Okay, now we're looking to tidy this thing up. We already know that we can go from sine to cos anytime we like, as long as we make up for it by taking whatever the angle is and making it 90 degrees minus that, or if we've got 90 degrees minus something, we can change it back. So at this point here, we can actually change this one back and say, hey, this is exactly the same as just the sine of alpha. Okay, so we've sort of come full circle there and made it much neater. And here, if we've got the sine of 90 degrees minus alpha, then we've actually just got cos of alpha and sine of beta. And that's how we end up with this one having cos and cos, sine and sine, and yet this other one having sine and cos together and cos and sine together of each other's angle. So we're pretty well finished that one now, and although it feels hard to get started, it tidies up nice and easily. And while we're at it here, we might as well keep going and prove sine of alpha minus beta. We need to just replace beta with minus beta and vice versa. I've written it slightly different there this time. Okay, so we've got our expression here for sine of alpha plus beta. All we need to do then for this one with alpha minus beta is we need to replace any betas with negative betas. So we get sine of alpha cos of minus beta plus the cos of alpha sine of minus beta. Now we've got to consider how we tidy these up, and we've considered this already, we just have to do it all over again. So we can do it over on the side here to save a bit of space if we like. So we can say that cos of negative beta equals the cos of beta. How do we know that? Because cos is even. Okay, and the sine of negative beta is equal to the negative sine of beta, and the reason we know that is because sine is odd. Okay, and that's enough probably to say it like that. So that means the cos of negative beta just is the cos of beta, and that one tidies up really easily. And over here, cos of alpha will stay the same, but this is going to become negative sine of beta. So the negative sign can come all the way out the front here, and we get this. So now we have this one done. Okay, for the last one, all we really need to do is consider how do we ever find tan if we've got sine and cos? Well, we know that tan of anything is equal to the sine of that thing over the cos of that same thing. So since we've already found identities for sine and for cos, alpha plus beta, we can do the same for tan by literally just saying that the tan of alpha plus beta must be equal to the sine of alpha plus beta over the cos of alpha plus beta. And now we've got expressions for both of those. We can just sub them straight in. So the sine one, I always remember it starts with sine alpha and then does sine and cos together. And I remember that whatever sign is there, it has the same one in it. And then I go and write the other two things together that I haven't used yet, like that. And I remember that for the cos one, we've got cos, cos, sine, sine, and the sine is different in the middle. So I know I'm going to have cos of alpha, cos of beta, minus sine of alpha, sine of beta. Okay, now we need to tidy this up and get it as good as we can. Now, it makes sense to divide all four terms by something that will allow us just to tidy things up a little bit. So if we go ahead and divide everything, all four things, by cos alpha, cos beta, now why have I picked that? Well, it just sort of works out nicely. Then on the top here, when I divide this by cos alpha, cos beta, the cos betas are going to cancel out and make 1. And the sine alpha over the cos alpha is going to make tan alpha. Okay, so we're sort of bringing it back to being all about tan. Let's write down what we're doing here. Next, we're dividing by cos alpha, cos beta. which is the term that's down the bottom here, okay? Now to remember which one to divide by, I sort of know, and in fact you've got these on your formula sheets, I know that down the bottom of my fraction I've got a 1 there. So that reminds me I need to take that and just divide it by itself. Okay, so for generating the proof, I mean you've got these things on your reference sheet, but when it comes to proving them, you want some little reminders that make it easy for you to remember what to do. So next, if we divide this by cos alpha, cos beta, the cos alphas are going to cancel, but I'm going to have sine beta over cos beta, so that's going to be plus the tan of beta. And now to the bottom, I've got something divided by itself, so that gives me 1. And here, sine alpha, sine beta over cos alpha, cos beta gives me minus tan alpha, tan beta. And I'm done. So that's that one finished. Okay, now while we're there, let's go ahead and prove tan alpha minus beta. So that's a bit of a bad alpha there. Now what do you think we're going to use? It seems pretty obvious because we've done it twice before. We're going to just swap the betas and the minus betas. Okay, so when we go ahead and do that and write out this formula here, we're going to get the tan of alpha minus beta is equal to, now we've got the tan of alpha, that stays the same, plus the tan of negative beta over 1 minus tan alpha, tan negative beta. Now at this point we want to tidy it up, so over on the side we'd want to write something that we know about tan beta, tan of negative beta. Tan of negative beta equals, now what does it equal? How did we figure it out with sine and cos? Didn't we think about the oddness and evenness of the curve? And if we think about the tan curve, we've got something like this. We know that if we find the tan of, say, 45 degrees or the tan of negative 45 degrees, it's the same number, but a negative sign out the front. So that reminds me that we've got the negative tan of the same thing we would have had, its positive counterpart, because tan is an odd function. Okay, so you can write that in your proof. So that means that you can tidy it up even more on the next line and replace both of these tan negative betas with the negative tan of beta. Now what's that going to do up here? Negative tan beta, it's going to bring a negative sign in here, isn't it? So on our last line, we've got tan of alpha minus the tan of beta over 1. And here, if this is the negative tan of beta, it's going to change that sign there to be a plus. So just like with our other examples, it's not enough to just start with this formula and say, I just changed the signs. That's not enough. What you need to do is change beta to negative beta and then reason about what tan of negative beta really is, make that substitution, and that is how you generate the proof of that formula. And that's all 6 of them now proven. Remember, we started with this one and we worked our way through.